In section 11.1, we were introduced to the idea of differential equations, and in section 11.2 and 11.3, we discussed Euler's method and slope fields and the idea of equilibrium values. Section 11.4 is about separation of variables, which is a powerful technique for actually solving a differential equation. In other words, if we start with a differential equation, is there a way to go about finding an actual solution? So we'll begin by taking a look at a simple example, dy dt equals 0.5y. This is the same as saying dy dt equals 0.5y of t. T is the input variable and y is the output. So we're trying to find what y of t is. We're trying to find a formula for y in terms of t. And we're going to assume the initial value that y of 0 is 2. In other words, when t is 0, y is 2. So separation of variables is a technique whereby we put all the y terms on one side and all the t terms on the other side of the equal sign, including the differential terms dy and dt. Now, in Calc 1, we would never treat dy over dt. We think of it as dy dt. We would never treat this as a fraction. But separation of variables is a method that allows us to do so. The formal theory behind it is beyond this course. But what we'll do is we will take this and we will put all the y stuff on the left side and all the dt stuff on the right side. So if I divide by y, I get dy over y, and if I multiply each side by dt, I get 0.5 dt. So all of the y stuff is on one side, all of the t stuff is on another. We have separated the variables. To get rid of the dy and to get rid of the dt, we integrate each side, indefinite integrals. If we integrate dy over y, we get the natural log of the absolute value of y. And if we integrate 0.5, we just get 0.5t plus a constant. There's actually a constant on the left side, but we can just sort of clump that together with the constant on the right side. Now, to figure out this constant, we use the initial value. We know that when t is 0, y should be 2. So if we plug 0 in for t here and 2 in for y, that tells us that c is the natural log of 2. So we know the value of c. Now we want to solve this for y. The difficulty is that we have this absolute value. So let's talk a little bit about that. In class we discussed the notion of equilibrium value. The equilibrium value is determined by setting the dy dt term equal to 0 and solving it for y. If I set dy dt equal to 0 here, I get y equals 0. That's our equilibrium value. A solution can never cross an equilibrium value. Okay, so we know in our case that y starts above the equilibrium value because y of 0 is equal to 2. So that means our solution is going to start up here at 2. And because the solution cannot cross the equilibrium value, the solution has to stay up here where y is positive. So if y starts above the equilibrium, it stays above the equilibrium. Solutions don't cross equilibrium values. So that says that y is greater than 0, so that the natural log of the absolute value of y is simply the natural log of y. This allows us to contend with the absolute values. So we had that the natural log of the absolute value of y is 0.5t plus c. We determined that c was the natural log of 2. We also know that we can drop the absolute values now because of the discussion we just had, which says that the natural log of y is 0.5t plus the natural log of 2. Let's solve for y by exponentiating each side. In other words, take this statement and write it in exponential form. And if we do that, I get y equals e to the 0.5t plus the natural log of t up here. Now, using properties of exponents and logs, I can simplify this. It's e to the 0.5t times e to the natural log of 2. But e to the natural log of 2 is just 2. So our final solution is y of t equals 2 e to the 0.5t. Let's take a look at another example. dy dt equals 2 plus 3y with the initial value, y of 0 is 0. So we get all the y stuff on one side and all the t stuff on the other side. So we divide by 2 plus 3y, and we multiply each side by dt. We have separated the variables. Now we will integrate each side. If I integrate dt, I get just t plus a constant. Now, if I integrate 1 over 2 plus 3y, if I compute the left-hand side here, I have to be careful and do it by substitution. U equals 2 plus 3y, so du is 3 times dy. This is a 3, which says that 1/3 du is dy. That means in terms of integration by substitution, I can take this integral and write it as 1/3 times the integral of 1 over du. That's 1/3 the natural log of the absolute value of u, which is 1/3 the natural log of the absolute value of 2 plus 3u. So that's the result of integrating the left side. The result of integrating the right side was t plus c, so here's where we're at. We know that when t is equal to 0, y is equal to 0. That was the prescribed initial condition up here. So if we take that, it allows us, and plug that in here, if t is 0, y is 0, it allows us to conclude that 3c is equal to the natural log of 2. Now, I could solve that for c, but here's a little trick to save us some time. I'm not going to. I'm just going to leave it like that. So here's what we have. We have that 2 plus 3y absolute value equals e to the 3t plus 3c. I simply took this statement right here, and I used properties of the exponentials, and I converted this to exponential form. So the absolute value of 2 plus 3y is e to the 3t plus c, which using properties of exponents is e to the 3t times e to the 3c, and e to the 3c was the natural log, 3c was the natural log of 2. So e to the 3c is e to the natural log of 2, which is 2. So I have e to the 3t times 2. That's equal to the absolute value of 2 plus 3y. Now, how do I get rid of the absolute value? Well, I know that when time is equal to 0, when t is 0, y is equal to 0, which means that when t is 0, 2 plus 3y is just 2, which is greater than 0. So 2 plus 3y starts positive, so it stays that way. That means I can drop the absolute values. So I have 2 plus 3y equals 2 e to the 3t. If I subtract 2 from each side and then divide by 3, I get my final solution. 2/3 equals e to the 3t minus 2/3. Example 3. dy dx equals x squared over y. So here I'm doing everything in terms of x and y. I'm not going to prescribe any initial value, so that means there will be infinitely many solutions to this differential equation. Let's begin by separating the variables. Put all the y stuff on one side and all the x stuff on the other side. In other words, cross multiply. So we have y times dy equals x squared dx. We have separated the variables. Now let's integrate each side. The integral of x squared is at 1/3 x to the 3rd plus c. The integral of y is 1/2 y squared. Now again, there would be a constant of integration on the left side as well, but we can just kind of clump that with the constant of integration over here. Now we need to solve this for y, not just leave it in this form. If we multiply each side by 2, we get y squared equals 2/3 plus 2c. If we take the square root, we get y equals plus or minus the square root of 2/3 x to the 3rd. Now what I did was I took this 2c And I basically just renamed it as c because twice an arbitrary constant is again an arbitrary constant. So that's why this 2c became c here. If you leave it as a 2c, well, that's okay. It's just neater this way. So we're going to be spending some time in class working on some applications of differential equations, looking at Newton's law of cooling, logistic growth of biology, various examples. What I would like for you to do for class are 3 examples. dy dx equals 2y plus 4. The initial value is y of 0 equals 1. dy dx equals y squared. The initial value y of 0 is equal to 1. And then dy dt equals y squared plus 1. For each of these, you should find y in terms of x, y in terms of x, y in terms of t. However, this third example does not have an initial value, so it will have an arbitrary constant. So please do these for the next class.